Hello everyone, welcome to another lessons learned video. Today we're going to go over some synthesis problems, and if you need to do them if you know all the reactions for Orgo 1, maybe you're trying to do some practice, or you need to know how to do synthesis problems, this is a good place to get some practice on it. And if you know the reactions, if you don't know how to approach synthesis problems, but you know the reactions really well, then this is a good place to also get started on that. So let's say that we have this molecule, benzene with a carbon and a chlorine attached, and we're trying to get, I drew it too big, so let me let's say we have this. So how do we get from the molecule on the left to the molecule on the right? Excuse me. So we see that we have to add some group and change the chlorine. So because even though chlorine is not a great leaving group, because this is benzylic, we could try water, and water would react through an SN1 mechanism, and it would basically create a carbocation here that, though it is primary, it's stabilized by resonance. Right, so it would basically kick out the chlorine and put an OH here. And maybe there's people saying, well, you can't do SN1 on a primary carbon. Okay, could use hydroxide as well, right? So either way would work. Now at this point, we want to add some carbons to this to this oxygen. So the way we want to do that is by adding sodium hydride. So sodium hydride, this hydride ion is extremely unstable, and it's very very basic, right? So it'll really want to react with something, really wants another hydrogen so it can turn into hydrogen gas. So it's going to take this hydrogen and leave this oxygen atom with a negative charge. Then at this point, we simply need to add carbons there, and we need to add 2 carbons. So since we have this is a bit of a big negative sign there, we have our nucleophile, which is this negatively charged oxygen atom, but we need an electrophile to attack. And we preferably, but to get the product, we definitely want the electrophile to have 2 carbons like this. So we can use basically ethyl bromine, as it's commonly called, so, or ethyl bromide. So if you were to draw, you could draw the structure a little better. So we can draw it like this, or like the way I did. And so this carbon would be the electrophile, right? It's going to have a slight positive charge due to the electrons being pulled a little closer to that bromine, and this oxygen is going to be like, woohoo, low electron density. So then it's going to attack that carbon, and the bromide ion is going to leave. And so now we have 2 carbons that are attached to this oxygen, which is what we want at the end, right? 2 carbons attached to that oxygen. So let's work on our next synthesis problem. So let's say that we begin with a chlorine like this. And let's say that we have a chlorine on this, and we want to end with a hydroxyl group on there. But it's the same orientation, so the orientation or the stereochemistry doesn't change. Now, if you were to do SN2 here, the issue is that it would do inversion of configuration. So if you were to add something like hydroxide, it would just it would simply invert the configuration, or not like that, but you know, like this, and then there would be a hydroxyl here, because the oxygen would attack from the opposite side of this chlorine and kick out the chlorine. But we want to be on the same side at the end, so what can we do here? We could still do hydroxide. And hydroxide would, in this case, yield two products. We'd get an SN2 product that looks similar to what we discussed, and not like that, like this. Right. And I kept drawing it wrong again. All right, it looked like this. But this would actually be the minor product. The major products of this would be E2. And the major product would involve a double bond. And so we want to extract out only the major product. Then we can use a process like hydroboration oxidation. And hydroboration oxidation adds a hydroxyl group on the less substituted position. So on this carbon, there would go a hydroxyl group. However, the hydroxyl group would be added alongside with a hydrogen on this carbon. And those two molecules, the hydrogen and the hydroxyl group, are syn, meaning that they are on the same side. And notice how here they're on the same side. That means that the methyl and the hydroxyl have to be on opposite sides. So we get the product we want. In this case, like that. So on this next problem, we have a bromine on this carbon, and we effectively want to move the bromine to a different carbon. So think of a way in which you could do this. So to achieve this, we first need to get rid of the bromine, but we want to form a double bond somewhere. Now, we don't want to form the double bond where it's going like this, because then we're moving away from our target area, which is this carbon. So we want to do it here, and we want to form the carbon between the double bond between the carbons that are more substituted. So we're going here, not here. More to get this product that we want here for the intermediate. So we get this product. We want to use sodium ethoxide can be a base we can use here. Right. And then to get bromine here, we want the bromine to be on the less substituted position. So in that case, you want to add HBr with peroxides. Now in this next problem, we have a six-membered ring with 2 extra carbons and a hydroxyl group. We want to actually make it so that we have a double bond inside the ring with the carbon skeleton looking the same shape. So because the double bond is inside the ring, you kind of want to move this way. Right? We want to move from this carbon to here and then here. So we want our functional groups to move that way. Since we have a hydroxyl right now, we can probably form a double bond once we react it with something. Now, one thing we could do is add TSCl, and this is going to add a tosylate group as opposed to the OH to make it a good leaving group. And then we can add sodium ethoxide, and this would form a double bond between these 2 carbons. And then we want to put some group on top of the double bond, so we can use a bromine. And the bromine would go on the more substituted carbon, which is right here. And now the molecule we could use is we can use really any molecule. We can use either tert-butoxide or we can use sodium ethoxide. I believe the outcome will be the same, but I would think that sodium ethoxide is a better idea. Slightly better idea because tert-butoxide might favor this reaction, where like the double bond would go here, because there's a little less steric hindrance than going into the ring and interacting with all this stuff. But in general, if you use sodium ethoxide, this product will be favored over this minor product. And the reason is because the double bond is endocyclic here, inside a 6-membered ring, and that's actually more stable than it being outside the 6-membered ring. So this would be major product. This would happen more often than this in the reaction. So hope that that helped you get some good practice on this, and thank you for watching.